Let's approach the structure theorem that I stated last time. I recall the statement somewhat later, but right now I want to prove a lemma. Which also was stated last time, but I recall the statement. Let G be a locally compact abelian group. And suppose that G is generated by a compact neighborhood of 0. Then there is a closed subgroup z to the power n in G such that the quotient of G over this subgroup is compact, and moreover this subgroup does not intersect this neighborhood V. Okay. So here I mean that there is some subgroup isomorphic to z to the power n. To prove this, I will need the statement with which I finished last time, and I recall it. Again, let G be a locally compact abelian group, and suppose that G contains a dense homomorphic image of the group of integers. So let's call this condition somehow. Let it be condition star. So we proved last time that if G satisfies star, this condition, and G is not compact, then G is equal to this subgroup of integers. So this will be used when we prove this lemma. And now let's start. I recall that this is about something specific inside our group, our abstract group. We may assume that this neighborhood V is symmetric. Neighborhood, I should call it somehow. So without loss of generality, V is equal to minus V, because simply we can consider the union of V and minus V. And now by induction we define the sets V sub n, so V1 will be equal to V, and if Vn is already defined, then Vn plus 1 is equal to Vn plus V. So this is an inductive definition, and since G is generated by this neighborhood V, we obtain the following formula. So G is equal to the union of these sets Vn for all n. Now we use the fact that V is also compact, not only a neighborhood of 0, but also compact. And then all Vn are compact, and for the moment we need only that V2 is compact. So V2 is compact. And from this it follows that there are there is a finite collection of elements of G such that this set V2 is included in the union of xi plus V. So if we consider arbitrary shifts of V, they cover G because V is open. So arbitrary shifts of V cover the set V2, but V2 is compact, and so there is a finite collection of such shifts of V that cover V2. Okay, and now consider the group generated by this finite set. Consider this group. I claim that V plus H is equal to G. Why? Let's prove this. So we shall prove by induction the following conclusion: Vn is included in V plus H for all n. So this is certainly true for n equal to 1 and 2. If n is equal to 1, then V1 is V, and H is a group, so it contains 0, so this is certainly true. And if n is equal to 2, then we have this inclusion. And okay, so again we obtain this one. And now, since it is true for n equal to 1 and 2, it is easily seen that this is true for all n, because suppose this is true for some n, then consider Vn plus 1. It is included in Vn. It is equal to Vn plus V, and this is included in V plus H. And this is V2 plus H, and V2 plus H, well, V2 plus H is equal to V plus, okay, so it is included in V, okay, this is V2, and V2 is included in V2 plus H is included in V plus H. So V2 is included here. So this is included in V plus H plus H, but H plus H is again H because H is a subgroup, so this is again included in V plus H. So this inclusion is true for all n, and hence we have this relation because the union of all Vn is equal to G. Now consider the subgroup generated by one element among those xi. Well, and consider its closure. If all closures hi bar are compact, then H is compact, H bar, because it is included in the sum of these groups hi bar. Then V plus H bar is compact, and this set contains G, so we obtain that G is compact. Well, and I remind you that our claim is that there is a closed subgroup of type z to the power n and g, so that the quotient is compact. But we have proved that under this condition g itself is compact, so then the statement is true simply with n equal to 0. So it's compact, and the lemma, not a theorem. Simply with n equal to 0. Now, so if G is not compact, then at least one of these closures is not compact. Well, suppose that E is such that HE bar is not compact, and then we are under these conditions. So our group HE bar contains an isomorphic image of Z, because it's generated by one element, and it is not compact. Then it is equal to Z. By the lemma proved last time, and it follows that even HE is equal to HE bar, because otherwise it's impossible. This is a discrete group, and okay. Okay, so we have obtained some subgroup of our group H which is equal to Z, but in fact we have proved a little bit more. We can distract from our setting and observe that we have proved even more simply. If G, here G probably is not the same group as in the statement. Any locally compact abelian group, if G is equal to V plus H, and V is as in the statement, some neighborhood of 0, compact neighborhood of 0 in G, and H is a finitely generated group. Then H contains an infinite cyclic subgroup. Okay. So we have proved this. And now we return to the situation. So we have a cyclic subgroup in our group H, and our H is finitely generated. So in this situation, take the greatest n, such that H contains a subgroup H prime isomorphic to z to the power n, to z to the power n. It is impossible that H contains such a subgroup for every n, because otherwise it would not be finitely generated. So such an n exists. Now consider the intersection H prime with V. H prime is a discrete group because it is isomorphic to Zn. So this intersection is finite. This is finite, and from this it follows that we can replace H with its subgroup H prime, subgroup of finite index so as to ensure that H prime intersected with V consists of the zero element only. Just that n is some lattice, so we take its subgroup, which intersects this V only by 0 because there are only originally there are only finitely made elements here. And now we take the quotient of G over this group H prime. Phi is a natural homomorphism. Okay. And now, what do we obtain here? So here we have, where is this equality? There. There, our G is equal to V plus H. Okay? Our G is equal to V plus H. Here it is. Then simply apply this phi. So G is equal to V plus H implies that phi G prime, this quotient group, is equal to phi of V plus phi of H. Now here again, phi of V is a compact neighborhood of 0 because phi is open and continuous, so this is a compact neighborhood of 0 here. And this is again a finitely generated subgroup of G prime, but this time this subgroup has no infinite cyclic subgroups, because otherwise this number n would not be minimal. If you find some infinite cyclic subgroup in this group, then we lift it by phi somehow. We lift the generator of it. And we see that this lifted subgroup can be added to this Zn to form Z to the power n plus 1. So phi of H has no infinite cyclic subgroups. And by this observation, I remind you that this observation is valid for every group, not necessarily for the original G, but for this one also. This observation implies that G prime is compact. And this is the claim of the lemma. This is the claim of the lemma. Okay. Now I need two more auxiliary statements, which are probably a bit less involved. And after I prove them, I can pass directly to the structure theorem. So the next lemma tell us the following. Well, probably it would be useful to enumerate them. So let it be lemma 1. And last time it was lemma 0. Now, lemma 2. Lemma 2. Let G be a locally compact abelian group. And let E be an open and compact subset of G. This combination of properties seems to be a little bit ambiguous, but in principle this may happen. For example, if we consider the dyadic group D infinity, or D, I don't remember. It seems to me that I denote it by D. So if you consider the dyadic group, it is totally disconnected. Totally disconnected. That is isomorphic to the counter set, and there are many compact neighborhoods of zero, compact open neighborhoods of zero there. There are very many sets that are simultaneously open and closed. Maybe a bit tamer example is the sum, direct sum of the circle and the group of integers. So it is the union of many disjoint copies of the circle, and each copy of the circle is simultaneously open and closed and compact. So this happens from time to time, but so this lemma needed for the most part to handle examples like the dyadic group, or to do something with total disconnectivity of some group or its subgroup, but also examples of this sort. So it's not so much strange. Anyway, we have a locally compact abelian group, and we have an open and compact subset of G. Then the following properties hold. First, there exists a symmetric neighborhood W of 0 in G such that we have this relation W plus E is equal to E. B, if 0 is an E, then E contains an open compact subgroup of G. So if this E is a neighborhood of 0, then we can replace it even by a subgroup which has the same properties, open and compact. And the last property, C, is that E, always E, is a finite union of shifts or cosets of some open subgroup of G. Okay, so this is fairly simple, of purely technical nature, but it will be useful. Now let's prove it formally. Let's prove it formally. Our E is open, so for every x in E, there is a neighborhood of 0 Vx. Such that I demand even more than you can imagine. X plus Vx plus Vx is included in E. This is because of the continuity of the sum. So we can even find so small neighborhood that twice this neighborhood plays this role. So this is true, but the sets of this form, x plus Vx, they cover E, and our E is compact. So there exists x1 and so on, xn in E, such that E is equal to the union of the sets xi plus vi, vxi. So we have this, and after that, as usual in such situations, we take simply the intersection of this vxi so take this intersection. W. Now, if we take an element in E and another element in W, then we can find some number I so that X is included in this set, surely, because of this inclusion. Well, and then X plus W is included in Xi plus V Xi plus W, and W is included in all Xi's, so this is included in Xi plus V Xi plus V Xi, and this is included in E by the choice of our neighborhoods, so this is an E. This is an E, and this is precisely statement A. There is a symmetric neighborhood W of 0. Well, I didn't ensure that this is symmetric, but simply we can, from the outset, take all our neighborhoods symmetric. Then we obtain symmetric W. This is A. Now to prove B, let H be the subgroup generated by this set W which you found in item A. Then H is open. H is open because H contains a neighborhood of 0 in the entire group G. So it contains a neighborhood of any point in the entire group G, so it is open. And since it is open, it is also closed. This I explained last time, because if you have an open subgroup somewhere, then its cosets are open and they are mutually non-intersecting, so the entire group splits into the union of different cosets, of non-intersecting cosets of our open subgroup. So it follows that all these cosets are also closed because the complement of each of them is open. So it is open and closed, and well, this is B. This is B. And as to C, this is also clear, because if 0 is not an element of E, then surely this subgroup will not be included in E, but in any case it will be a union of cosets of this subgroup, and so and the union is finite because all of them are closed, and E is compact. So we have proved lemma 2. Lemma 1, lemma 2. Now yet another lemma, which is not very difficult either. And even quite natural. Here I will use some term locally homeomorphic, locally isomorphic, but I'll explain what I mean. Probably it is better to state it first and then explain. Lemma 3. Let G be a connected locally compact abelian group and let G be locally isomorphic to the group Rn. If G does not contain infinite compact subgroups, then simply G is equal to Rn. Now I must explain what the term locally isomorphic means. This means simply the following. So locally this means the following. Simply there is a ball. There is a ball Q in Rn, centered at 0. And such that there exists homeomorphism phi from this ball to V onto and V is a neighborhood of 0 in G, so that its homeomorphism is also algebraic to a certain extent. That is, phi of x plus y is equal to phi of x plus phi of y whenever the 3 points lie in this ball Q, whenever x, y, and x plus y belong to Q. So really some homeomorphism in the neighborhood of 0, in Rn, and it preserves sums when this makes sense. And we must prove that then our group is isomorphic to Rn. And the condition, so there are two conditions, two basic conditions beyond this isomorphism, that G is connected itself, and also it has no infinite compact subgroups. So if it resembles Rn in these two respects, then it must be Rn. Okay. So proof. Clearly for every x in Rn, there exists a natural number n, so that x divided by n belongs to Q, because Q is a ball centered at 0. And for this x, so simply we want to extend our mapping phi to the entire Rn, and for such an x, we define phi of x is equal to n times phi of x over n. This is consistent. Because if we find some other index n with the same property, we shall obtain the same. So simply if x over m also belongs to Q, then we can write in this way: n phi of x over n is equal to n m phi of x over n m, and this is by additivity. If the element x over n is already in Q, so if we divide it further by something, it will be still in Q. And if we add m times this element with itself, then this additivity relation can be applied. Where it is? Where it is? Here it is. This additivity relation applies, and so we can write this formula, and after that we use it in a different order. Simply this is equal to m phi of x over m, again by this additivity, this time applied to this element x over m. So this is really consistent, and then we have extended phi to a continuous homomorphism which I denote by the same letter, again phi of Rn to G. Now this phi is an injection. Why? Because if it is not an injection, then there is an element, a non-zero element, a non-zero element, so that phi of x is equal to 0, okay? But if I divide this x by some large natural number, then I obtain something of which phi is not equal to 0, because locally near 0, this phi is a homomorphism. Then it follows that, well, there is n, so that phi of x over n is not equal to 0, but some multiple of this element is equal to 0, and this means that G contains a compact subgroup. Simply, the subgroup generated by this element will be compact. So simply G contains, then G contains some quotient of the group R, and the quotients of the group R, so this is circular quotient of the group R, this is a circle. So it is compact, infinite, and okay. And this is not the case by assumption. So it is an injection. It is an injection, but also phi is an open mapping. Because there's a homomorphism, and at near 0 it is open. It maps some neighborhood of 0 onto some open neighborhood of 0 in G. So since it is a homomorphism, it is an open mapping on the entire Rn, and it follows that its image in G is simultaneously open and closed and non-zero, and G is assumed to be connected, and then it follows that the simply phi of Rn is equal to G because G is connected. Okay. So somehow this lemma is independent from the previous lemmas. It is something from other direction, but also useful and required for the subsequent proof. And now I pass to the proof of the theorem. I recall the statement. Structure theorem. Let G be a locally compact abelian group, then there is N and an open subgroup G prime of G, so that G prime is the direct sum of Rn plus say K, where K is a compact group. Well, I explained this last time, but let me repeat these words. What is responsible here for the non-compactness? First, this Rn is responsible for non-compactness, and second, the quotient of G over G prime. This is a discrete group which may be infinite, so there are 2 points responsible for non-compactness. One of them is here, and the other is here. Otherwise, everything is compact. And moreover, there is something here also responsible for connectedness. First, this subgroup is connected. And as to this compact group, it may or may not be connected, or may not contain some connected parts. Say it may be a torus of some dimensions, and it is connected, and maybe a totally disconnected group like the dyadic group, or maybe it's some of the 2 groups of this sort. So connectedness is reflected in this term, and the combination of non-compactness and connectedness is entirely reflected by this term. And here also may happen to be something connected, but this is hidden. This may occur, may not occur, well, but now we start the proof of the theorem. Well, let first G0 be the connected component of 0 in G. Okay, so I remind you that a connected component of whatever is always closed. So G0 is closed. This is the reality. Simply because the closure of a connected set is closed itself. Then take an element x0, x in this G0, then x minus G is also connected because it's obtained by application of some homeomorphism from minus G0, sorry. It is obtained from the connected set G0 by application of some homeomorphism, so it is also connected, and also it is clear that G0 intersected with this shift x minus G0 is not empty. Because if it is empty, then what happens? Well, what if it is empty? Simply we have the set 0. The point 0 is here. The point 0 is here because G0 is a connected component of 0. So 0 is here, but also 0 is here because this G0 contains x. So it is intersected. This intersection contains at least the point 0, so it is not empty. And since we have two connected sets, then it follows that x minus G0 is included in G0. Because otherwise something will be bad. If it is not included, then it is not connected. Then it is not connected, and okay, not quite. If it is not included, then G0 would not be the connected component of 0. It wouldn't be the minimal connected set, the maximal connected set containing 0, because if it is not connected, then it can be enlarged by this, by adding this element. So we must have this. We must have this, and so the conclusion is that the connected component of 0 is a closed subgroup. Obligatory. In any group. So we shall use this, but at some point we shall use this once again for some other group in the process of the proof. So this observation will be used at least twice during the proof. Okay. Now it is closed. It is closed, and what do we have also? Consider this quotient. So this group is totally disconnected. This is a totally disconnected group because G0 is a connected component of 0. So if this guy contains a non-trivial connected set, then G0 would not be the maximal connected set containing 0 and so on. So this is totally disconnected. And as to totally disconnected groups, we can apply lemma 2 to them. Specifically, we can apply the point B. So look, please, our group is totally disconnected. From this it follows that, well, let me formulate it separately probably. Let F be a totally disconnected compact, locally compact abelian group. Then every neighborhood of 0 in F contains an open compact subgroup. Well, and this follows directly from B, because since our group F is totally disconnected, then there is a base of open and closed neighborhoods of 0 in this group and compact. Open and compact neighborhoods of 0 in this group. By B, every such neighborhood contains an open compact subgroup of G. So this is a consequence of B. And now let's apply it, this statement, to our situation, and it simply implies that there is an open and compact subgroup K of this quotient. So this is by that lemma. And now consider the canonical quotient mapping of G onto this quotient, G over G0 over this connected component of 0, and take the group G1 equal to phi to the power minus 1 of K. So this is a complete pre-image of this compact group K. Now, what can we say about this G1? So let's observe the following fact. This is a triviality. K does not contain open subgroups of finite index. Of infinite index, so sorry, of finite index that groups of finite index surely exist, for example, K itself, but of infinite index. Because if we have such a subgroup, then its cassettes cover K, and since it has infinite index, this is in contradiction with the compactness of K. It is not covered by a finite number of cassettes of such a group, so all open and compact subgroups all open subgroups of this K have finite index, and this implies something about G1. We observe that every open subgroup in G1 contains G0. This is again because of connectedness, because of G0 is a connected component, the connecting component of 0. If you have an open subgroup of G1 that doesn't contain G0, then it splits G0 into two non-intersection, two open subsets. So this contradicts the connectedness of G0, so if we have an open subgroup here in G1, then under this mapping phi, it passes to some open subgroup of K, and there it has finite index. So the conclusion is that G0 is also free of open subgroups of infinite index. G0 doesn't have open subgroups of infinite index. So this property passes from K to its not G0 but G1, sorry, G1. This property passes from K to its inverse image. Now, probably what to do. Let me erase the statement once again. Now also I remind you that phi is open. And as any quotient map in the theory of groups, as any topological quotient maps, it is open. And from this it follows that there is is a compact neighborhood of 0 in of 0 neighborhood V, say V of 0 in G1, so that phi of V is equal to K. I remind you that K is an open compact subgroup, so it is lifted as some open compact set. Now let H be the subgroup generated by V. Consider the subgroup generated by V. This is an open subgroup in G1. Well, sure it is in G1 because everything lies in G1, and H is open because it is generated by some open neighborhood of 0. A subgroup generated by an open neighborhood of 0 is clearly open itself. And also H intersects all cassettes of G0 in G1. This is simply a consequence of the origin of this H. So what are the cassettes of this G0 and G1? These are precisely the points of K. You know, each point of K corresponds to a uniquely determined cassette of this group G0, yes, in G1. So these are the points of K, and we have the following relations, that phi of V is also equal to K. So from this and from the definition of G1, it follows that we really have these properties. This property H intersects all cassettes of G0 in G1. Well, and again, G1 is connected, and all cassettes of G0 is connected, and all cassettes of G0 is connected. So all cassettes of G0 are connected. So since they are connected, H cannot split any of these cassettes. So all of them are included in H. And this means that simply H is equal to G1, again by connectedness, argument. Well, and now we are in a position to apply some preceding lemma. Well, what do we have? We want to apply lemma 1. So we have obtained the following fact. So H was generated by some compact neighborhood of 0 in G1. Yes, and then we see, so G1 itself is generated by some compact neighborhood of 0 in this group G1. And then we see that we are under the conditions of lemma 1. And now we can find some index n and some subgroup of G1 equal to Zn, so that this quotient is compact. So by lemma 1, by lemma 1, G1 contains a subgroup isomorphic to z to the power n for some n, so that G1 over this subgroup is compact. Well, so we have found at least something specific in a fairly general group without any additional assumptions, so some number n. And now we pass to dual groups. Let me erase something. Maybe I'm going to erase lemma 3 because it is fairly transparent and the statement is self-suggestive, so probably I don't need to have it on the blackboard. Okay, and precisely here we have this lemma which we have applied. So this quotient is compact, and okay. Now consider the dual group of this G1. Let gamma be G1 hat, the dual group. Then by some duality, a statement if we consider the quotient of this, so let it be gamma 1 over some discrete group, we shall obtain the torus t to the power n, where D is the discrete group dual to G1 over z to the power n. So this quotient is compact, its dual group is discrete, let's call it D, and then if we take the dual of G1 and take its quotient by D, then we obtain the dual of this group z to the power n, that is Tn, the torus of dimension n. So again, gamma is something, D is something discrete, and the quotient is a torus. And from this it follows that gamma 1 is locally I did not say, I forgot to say that this group Zn also has a property which is written here on this blackboard. Let me write it down here. So this Zn intersected with this neighborhood V is equal to 0. Well, okay. So gamma 1 is locally isomorphic to r to the power n. Why so? Because this torus is clearly locally isomorphic to r to the power n. So if you take a neighborhood of 0 on the torus, or probably neighborhood of 1 if you write it multiplicatively, then this neighborhood is isomorphic to some ball in Rn. And here we have also the quotient of this gamma 1 over something discrete. But this discrete group, since it's discrete, it does not, this factorization does not involve some small neighborhood of 0 in gamma 1. So let me draw some picture. So the points of our discrete group, they are all separated away from 0 because it's discrete. And so if we take a very small neighborhood of 0 in this gamma 1, then this quotient map will be a homeomorphism on this small neighborhood of 0, and it maps this small neighborhood onto some neighborhood of 0 in the torus. And in the torus, this neighborhood of 0 is isomorphic to some neighborhood of 0 in Rn. So this is really a local homeomorphism of our group gamma 1 to Rn. Okay, we want now to apply the lemma which I erased, and in this lemma we needed that the group locally isomorphic to Rn be connected to make the conclusion that it is Rn or something like that. And here gamma 1 is not necessarily connected, of course, but let's take the connected component of 0. Let gamma 0 be the connected component of 0 in gamma 1. And this connecting component of 0 is a closed subgroup, of course. Okay, so it is closed. This is from some general statement, but also it is clear that it is open. It contains a neighborhood of 0 because by the fact that gamma 1 is locally isomorphic to Rn, so some neighborhood of 0 in gamma 1 is isomorphic, is homeomorphic to a ball in Rn. This means that this neighborhood of 0 in gamma 1 is connected. And since it is connected, it must be included in gamma 1. So this group gamma 1 must also contain some neighborhood of 0 this group gamma 0 must contain some neighborhood of 0 in gamma 1, and since it contains a neighborhood of 0, it is open. So again, gamma 0 is open by a connectedness argument. Okay. Now we recall that this G1 contains no subgroup. I remind you that this G1 contains no, where it is, this was written somewhere, no subgroups of infinite index. Where it is? Here. G1 does not have open subgroups of infinite index. This we have proved. And this gamma 1 is the dual of this G1. So G1 has no open subgroups of infinite index by duality. This means that that gamma 1 has no infinite complex subgroups. Well, why this is so?